some X and containers today. Not quite such a new topic, but we'll see what happened for a few last months. It may be interesting. I also changed my setup a bit, so we'll touch it a little. So who am I? I work at a company named Bellsoft. It's one of top OpenJDK contributors, and we create our own TCK verified distribution of OpenJDK. So I'm a performance architect. I participate in development mostly in x and AR64 ports, but not only in that ports. I previously worked at Oracle in performance team, so you probably know my ex-colleagues. So here we are with contributions. I mean, our company. And what about containers? Are they good or bad? It depends on how do you use them. And let's see. So today it's not 2019, it's 2020, awful year of total online. And yeah, it's still like this, except, I don't know, I get my ex not in grocery store, but mostly the delivery guys. That's how it is. And still, you expect that when you look from outside, that everything just works. You use containers, use other technologies, nothing breaks. All services that you've put, that you deployed, still present in your deployment, but it may be not so. So what about technologies that we use? Yes, we use good technologies to help us. And help is that we want to isolate different parts of our deployments, and we want to reproduce the results that we've tuned, services we've tuned in development and in testing. We want to be sure that they behave and get the same virtual environment in production. And we don't need real virtual machines for that, because real virtualization is quite a heavy thing. It consumes a lot of resources. It slows down your application because you waste resources to get the highest level of isolation. And you don't really need that. You just need to isolate your configuration, to emulate basic things. Operating systems provide such a mechanism for you. So in Linux, it's called Linux containers with groups and namespaces. And that allows you, without using any additional technologies besides what you get in basically your Linux distribution, that allows you to create some kind of containers. So you can configure your C groups and the star processes with the resource trees and kind of isolation and resource limits. That's what OS gives you. And there are tools above that manage and automate that process. So they hide a little bit of complexity, and they hide OS specifics, and instead give you a concept of a container as a thing that you can use to start some, not playing with operating system, but playing with this tool, which manages configuration and gives you more understandable concepts of what you really want to manage in the first place, like CPU and memory sources, port mappings. That's it. So a good example, of course, is Docker, and we'll be using this one. And here, then we work with such systems Your goal is to bring your application and its files, resources somewhere. So you need means to create so-called images, which basically are configuration that describes how your application interacts with other parts of the world, what files it contains, so things like that. And of course, there are tools even above that, like Kubernetes or Swarm or whatever, that glue together different parts already being Dockerized or containerized. And what happens if we just put some application in a container? Well, it probably works, because even if we don't do that, we still have kind of container 0, which has its own tree of all resources, and it's just managed by operating system. But you, as a creator of such thing as your application and container, must provide some hints or must use any tools that help application to live in container. Because otherwise it will just ignore what happens, and well, something not very pleasant may happen with the application and with what you do. So Java is, of course, is just an application, but there are two tiers here. So first, then we write our business logic. We create our class file or jar file, which is probably rather small, especially if we talk about something called micro, like microservices. And this is a small part of what's actually being run. So, of course, there is a part with Java Virtual Machine that's able to execute that hello world. And also there are libraries that that also help the application to run. Of course, we use libraries. That's a strong thing in any ecosystem. And that big part, JVM, also consists of many interesting parts that have their own behavior. And even, for example, if your application is single-threaded one, you still have many threads in your JVM that run concurrently, that require some resources. And a lot of things happen. Like garbage is collected, your code is cheat compiled even for hello world. Of course, interpreter works. So all JVM parts work together under the hood and to run the application. And if you put all that construct into a container, of course, it all works in container. So what changes then? Well, we expect that everything will work just as it worked without any containerization. So we'll be able to use any tools that we have used for diagnostic before. We'll be able to debug our application. We'll be able to monitor how it behaves. And also, we expect additional properties from putting our system into container. As I said, we want to reproduce the environment that the application expects to see, that we've tested in test environment, and that we've tested in development. And we want to bring easy configuration of what we use, how do we map internals of the container and to the external world. And this work started in JDK 9 from very obvious and important things. support for limits that are set for CPU and memory. And memory limit is especially important, as we'll see today in a small demo. So then we run application in the container. It sees all the resources of the machine. So if it thinks that, okay, I have the entire machine, I have all the CPUs, and you start several such applications, you probably have much worse performance because you share each CPU by many threads. So they start switched frequently, and you don't get enough CPU resource, and you just waste your machine power. And of course, then you start to work with some Java applications put into containers. They actually must work. They mustn't crash. Then you use default garbage collector, which is G1. So, yeah. And then the same, what I described for CPU is applicable to memory limitations. We need to share all machine memory between different containers. So in JDK 10, the support has been extended by fine-tuning from usage, and the work started to support JDK tools that work with running JVMs for some diagnostics and control. And support for CPU limits has been extended with new flags, and some previous work has been reworked. And all this continued in JDK 11, where finally CPU limits has been supported fully, so you can use any kind of setting CPU resource limitations using, for example, Docker or any other system. Also, some deprecated flags were removed. New diagnostics has been introduced, so you can get basic information about your container using Java command line. And finally, CMD are working, which is really useful if you work with real production systems that you need to control or diagnose using that tools. But wait, we're still in 2020, and we still discuss Java 8 on Java conferences. Of course, because that's the best JDK ever. So JDK 8 had no support for containerization after the box. And this support has been backported from all subsequent releases up to 11, which means that different versions of different updates of JDK 8 got different set of flags, different functionality, and it is really much better to use the latest update of JDK 8 to get basic containerization support, to get it not put in its pants. And now it's JDK 14, and JDK 15 will be released probably next week. So you see a lot of things happened. Well, let's see in a bit more detail what things do we have extra. So there's a nice thing. Then GC returns memory to operating system if this memory is not used by your service or application. Logically, if GC sees that Java heap memory is free, it may return it to operating system to make it available to other services. So this allows you to have more dense deployment, more intensive memory use. Then you share your machine, then it's shared by many services, deployed in containers, for example. And you may have some running containers with your physical memory or limit what you have, because some consumers of that memory, they just don't use the exact part. Like if you have two services, one may use less than 1/2, so another may use more than 1/2 of that memory. And you can set a limit for both to more than 1/2 of the entire memory that you have. So few garbage collectors do that. It's G1, ZGC, and Shenandoah, all available in the latest versions of Java. So support in default garbage collector G1 has been added to JDK 12. And in upcoming JDKs, so if you look at this slide, all issues listed here are still not implemented, except Elastic Metaspace, which is pretty close to being targeted into JDK 16. So after the release, probably it will be available into mainline, which is pretty cool. And this Elastic Metaspace JEP is also about giving back memory to operating system, but not from heap, but from Metaspace. So the same idea, if you, for example, unload a lot of classes that you don't need anymore, you can give that back, that memory back to operating system. And also what's missing for a user is, of course, better diagnostics, better usage of information about your real memory structure, like support for NUMA. It really depends partially on what base image provides you, but also what we can get from Linux container subsystem, what information we can get and use, for example, for more performant garbage collection or better allocation of objects. So some work in Hotspot and some work in mission control. And also what has been just dropped into JDK 15, it is support for cgroups v2. So the usage of newer and more extended mechanism to getting cgroup information inside Hotspot. So that's how we get a pretty comfortable thing, not just bare metal boxes, but something we can live with. Okay, please feel free to post any questions. So I'll try to answer, or at least in the end of the session. So when we develop application, we not just write code, we plan how it will work, we plan testing, and we choose technologies and libraries that we use. And when we have all that, we use containers in testing, in development, in production. We have some CI/CD pipeline. And inside the container that we deploy, we have multiple tiers. So we have the most basic tier of so-called operating system, where we have native libraries, necessary packages installed, command line tools, so everything that looks like an operating system, while we still run on host operating system. But in a container, we pretend that, okay, it's slightly different to us. And then we have a level of JVM and its tools. So where we have all the modules, if command line tools, if we need them, all the things. And we have a tier of libraries, of course. Typically, it may be our container as in a sense of Spring and other similar technologies. We may use other libraries as dependencies. We will have typically rather small tier of business logic, because we use a lot of libraries and we write some code, leaves them together to get processing that we really need for our data. So where do we get that base layers? So we need to build some container using technologies that we know, but we cannot just take, for example, any arbitrary Java distribution and put it in a container. We should be aware about the license. We should be aware about who produces that image, how it is updated, what's inside, does it change, and all other stuff. So, for example, you can get Iberica JDK from regular Docker Hub. So you can just use a base image of Iberica. And you see that, so here, for example, is JDK 13, but JDK 11 and 14 is even smaller for Alpine. So the typical sizes of container images, then you create them in your registry. And you see that there is JRE and there's also JDK for 8. JRE for 8 is smaller, but you really don't need JRE for 11 and 14 because you have JLink. So you can create smaller images and custom runtimes for your application, or you can use predefined smaller runtimes that we provide you, and we'll see it in a small demo in a while. And it can be as small as 42 megabytes, and actually 41. So why do we have, how do we get such small images? Because we are using here Alpine Linux, which is a rather small Linux that only takes 4 or 5 megabytes of a static footprint. And it's also a peculiar thing because it uses different C library, standard library, not glibc, but muscle instead. So it is smaller and it's somehow different. It doesn't contain some functions of glibc, which is especially interesting. And there is a binary incompatibility. So if you take some binary program that is linked to glibc, for example, regular build of JDK, Hotspot, it won't work in such a system where standard library is muscle. But you can recompile that program. It requires some tricks and hooks, configuration and testing, of course. This way of using smallest Linux has been implemented as a separate project on OpenJDK called Project Portola. And our company now drives a Java enhancement proposal to integrate Project Portola into JDK mainline, which will allow to get small images, Docker images with Java, not from downstream from a project repository, but from the main OpenJDK repository. And that will unify what different companies do in this space. Currently, this implemented and tested for JDK, for latest JDK, which is now 14, soon it will be 15, of course 11, but also for JDK 8. Then the support will be integrated into mainline. It will be probably for current JDK at that time. I hope it will be JDK 16, but I don't guarantee that. Sorry. But even now you can get Alpine muscle builds for older JDKs. So I'll share the terminal window now. Let's see. So here I have. Is it fine? Can you see the terminal? It's thinking. Yeah, great. Thank you. So we'll build such an image. Literally easily. I just cleaned here my local repository, and then I use Docker file from a special Docker file that you may find here. I'm sorry, not for Docker, but if you go to Docker Hub and into Bellsoft profile, and you'll see Alpine muscle there. There's an instruction how you can get a Docker file and to include it in your Docker build process. So for example, then you put your application and invoke Docker build. You can choose predefined runtime variant of base, which is the smallest runtime that allows you to run like command line Java programs, to light, which is suitable for most kind of server applications, and it is less than 100 megabytes, and full, which is still pretty slim. It's, if you run Docker build, well, create a tiny container using the Docker file. You'll see that it's only 41 megabytes. Of course, then you add your application, it will be slightly larger, but it depends on your application this time. Okay, so it has been created. This is some remote Amazon instance. Okay. If you see, it's only 41 megabytes. So please check Docker Hub. Just try to show you that right now. Let's share the screen, for example. Okay. So, okay, here is Docker Hub with Liberica. And if you go here, Liberica OpenJDK Alpine muscle, you can find the instructions on how to use that feature and Docker build process. Okay. let's do our presentation for a while. So we've seen how to use Docker build features. Now we have a fresh Alpine Air, and we combine our small containers and our deployment. So then you have small footprint of your container. You have very good benefits of that. Set up new instances, for example, in some public cloud. So you do it much faster because your base image is much smaller. You spend less traffic, less wall clock time, less CPU time. You just get a small base image and then you deploy it. It also happens in environments then you update your containers, but you don't use layered approach to building containers. Sometimes you need to kind of certify the entire container, but not layers. It's simpler to bypass layered approach. Okay, let's look at some fun examples in a demo. I'll switch back to the terminal, and we'll quickly see how we can break our container and to diagnose what happened and to fix it. So as I said, I'm connected to some remote instances that are AWS, ARM, by the way. So there I deploy some service. Here I have diagnostics for that service and Docker stats. So this host has Docker, and I'll try to run my service and that using that Docker. I have another instance which does health checks. It tries just to connect to my first instance via HTTP and to get health check information and to connect to one of services that's embedded that sample service that we deploy. And it is very simple. It's just one endpoint and Spring actuator, and it gives us like 17 megabytes in a jar file. And I also have that host a JMeter that we'll try to use to put some load on that service. So as I said, here's a jar of 17 megabytes. It uses Spring 2.0, not the most recent one, but things are still more or less the same. So what we'll do, we'll try to run that. Not using any Docker stuff, we'll just use java-char and then the service, and then it starts. That's pretty cool. It starts in probably 5 seconds. Slightly less. I used to show that demo on slower instances, but this is not so bad. 5 seconds. Yes, it's not native image, but why not? So if we look at health checks, we see that the service responds to us and it has diagnostics that says that it's up. That's great. Let's stop it. Now we'll try to use Docker. We'll say, okay, Docker is a great thing. We can limit resources that we use. Let's give it only 5 megabytes of memory. And what will happen? It just didn't start. But we need some diagnostics to check what happened in fact. So we have system tools. Like we have journal.ctl, where we can check that memory came and killed the service because it exceeded memory limits. That's sad. But what's unusual for us as Java developers is that we saw nothing from that program. It didn't say that it's going to be closed. It just closed up silently. If you look why it happened. So here I even add some memory. It's because it tried to use all the memory that's available on this machine, or physical memory. But we said the operating system, don't let this application to use more than like 5 or 10 megabytes of memory. And that exceeds that limit, it's killed. But if we try to start this application without Docker, but just giving it very small heap size, what will happen? It instead tries to start and prints some exception, probably based on out-of-memory error. So we have runtime error inside runtime, and runtime handles it. It's not forcibly closed. It just limits itself. It says, I reached my own limit. I am not able to continue. I will close. So that's a big difference. Please remember about that. How do we know how much memory do we need? Well, we can use very good diagnostic features of JDK. Like we can use Java native memory tracking. We should run that application inside or not using the container, diff additional flags to check at some point that's clear for us how much memory does this application use. So let's do this. The application has launched. Now we can run the command. You see, we got the bit of this application, and we run J command and ask about native memory used in that application. So here, if we estimate what actual live heap do we need, and then we summarize it, the memory used for other internal parts of that application, we can calculate the amount of memory required to run the application. So in this case, it's like over than 500 megabytes in this configuration, this set of flags. But what I typically do in this demo is I say, okay, I'm greedy, I can limit the execution, try to limit memory much more. I leave it only 128 megabytes and say it will run. Then I say, okay, let's disable swap, and and after that it's not able to run because we really have 128 megabytes as a limitation. So you can see, okay, we are limited, and the application fails to start. And if you look at the same journal, you see it has been killed. What happens if we try to leave that swap here? So it is an AWS instance, and we even may explicitly say like memory swap 1 gigabyte, sure, but it still doesn't start, and it's still killed. Why does it happen? Because you see that warning, like your kernel does not support swap limit, blah, 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 blah. And that means that in case of this kind of instance, we really get a situation that swap is not enabled. So even then we try to provide such a configuration, then we allow Java application use to be swapped, which is really not a good practice, but still we might want to use that. That won't happen. Application will be closed. And to avoid that, we must follow the instructions for EC2, how to enable swap for C groups. There's a separate page for that. I can show you. Okay. The chart. So it's called container swap. And there's a description how to enable that feature. There are some steps, you must provide some resources, and then it will be picked up by your container system. Okay, let's get back to our service. What else can we do? Yes, we can try to put more memory, and we see that now it starts. Not so bad in a container, and still takes almost 5 seconds to start. You see it starts to use memory, but then we can try to put some load on it. And you see that the amount of memory it uses start to grow rapidly. So it will grow for a while, and then the service again will be killed by out-of-memory killer. And the same happens, but slowly, if I have swap enabled, the service will just become very slow, not responsible, and then it will be killed in some unexpected moment. Then swap actually shared by different Docker images will just be entirely occupied. Okay, let's won't wait for it, just close the service. So we can use newer JDK 11, and we can also limit the execution to only one compiler, C1 compiler, which produces simpler code and will use less code cache. And then we'll be able to run in 256 megabytes of memory. And you see that we also start pretty quickly, right? We just start in less than 3 seconds. And then we use Docker stats. And you see we actually occupy almost just half of that memory. So we might use less. We can also use even less memory by using application class data sharing and extracting our library classes out of the fat jar to use fin jar. And in the end, we can run something like this. So we disable swap, we use latest OpenJDK, Liberica OpenJDK, Alpine, Linux. We just use C1 compiler, and we use application class data sharing available since OpenJDK 11 as an OpenJDK free feature. We use some class path to run because we extracted the libraries. We don't use fat jar. And here we start only in 2 seconds. So very fast. And we also occupy much less memory. You see, it's way above 100 megabytes. All right. So what we have seen so far. Let's get back to the presentation. This in that services may break because, and most typically break because they have not enough memory, but we can diagnose that using system tools or Docker tools, and we can tune that and analyze how much memory do we really need in our scenario by using native memory tracking. Swap, please check it. If you're not sure, just contact, for example, me or our company, and we'll help you. We have some kind of internal checklist for checking what happens with services. And of course, use Docker tools like Docker stats, but not just Docker. You may use operating system tools like JStat or PMAP to diagnose your running service. And you can also use powerful features of newer JDKs, like application ahead of time compilation, which doesn't help in this case, but still you may use the slide as a guide how to enable it in your case. And application class data sharing, that allows you to use less memory and to start much faster with newer JDKs. So here numbers are slightly different, but yeah, the same. We greatly decreased the memory necessary to run our service, and startup we decreased from like almost 5 to 2 seconds. So also more than 2 times. So please don't be afraid. Report all the issues back to OpenJDK community, and happy running your applications in containers. Let's get to the questions if we have, I don't know, 1-2 minutes, if it's fine. Okay, I see no questions in the chat. Yeah. Okay, then thanks everyone. See you here on the conference. Bye-bye.